So now, we want to calculate the number of moles of this and the number of molecules, right? So now, remember, this whole thing is the compound. Well, we're going to need number of moles equals given mass over gram formula mass. We know our given mass is 124.7 grams. We need our GFM of this, and this is going to be hard. It's not hard, but it's time consuming. So start by just listing all your atoms. We have zincs, phosphorus, oxygen, hydrogen, and oxygen. And you're going to need to be able to count atoms in here, right? So let's see, how many zincs do we have? Well, this 3 goes with that zinc, so I have 3 zincs. Okay. Phosphorus. I have 1 phosphorus inside, but I have 2 of them, so this is 2 times 1, so I'd have 2 phosphorus atoms. Okay. Now, I've left these oxygen atoms separate, and you'll see why later in the unit. I want you to do that also. All right, so here we have 4 times 2, we have 8 oxygen atoms. Here we have 8 hydrogen atoms and 4 oxygen atoms. And this is to the 10th place again, so, oh man. So this is going to be, zinc is 65.4. Phosphorus is 31.0. Oxygen is 16.0. Hydrogen is 1.0 and 16.0. Oops. So this will be 64.0, 8.0, 128, .0, phosphorus would be 62.0, and then 65.4 times is 193.2. We have to add that all up. So 193.2 plus 62 plus 128 plus 8 plus 64 equals 455.2 grams per mole. All right, so then we bring this over here. We get 0.27 This should have probably 3 sig figs, 274 moles. Now we have to convert that to particles. So we take 0.274 moles. For every 1 mole, we have 6.022 times 10 to the 23rd particles. .65 times 10 to the 23rd particles. Okay, so these are just some typical problems. All right, so make sure you understand what's going on here with this hydrate. Okay, just remember that's one big formula. All right, good. We've done all of that. All right, our Our next little math thing that we have to do is called percent composition. And this is another easy formula. Our percent composition equals the part over the whole times 100. And sometimes you see it this way, percent mass of the element over total mass times 100. These two things are the same thing. They're just percent composition. So this is percent mass, percent comp. Okay, they're just part over whole times 100. And there's a couple ways that we can do things here. All right, so if we're just given a question like this, calculate the percent mass of oxygen in glucose. So we know glucose is C6H12O6. And what this is saying is, look at what percentage by mass of oxygen is this of this compound? Well, the mass of the percent mass is really just the part over the whole times 100. Now, I don't give you any other numbers. So if you're not given any other numbers, or you're not doing it like a lab procedure, we're going to use the GFM, or the molar mass. And since we don't have any other numbers, we're just going to round to the nearest whole. So now, when we look at this, I want to know oxygen, what percent of oxygen is in this whole thing. So oxygen has a mass of 96 grams per mole. The whole thing for the whole compound is 180 grams per mole. And we multiply 100, and we turns out that it's about 53%. Okay? So in this problem, this is my part, and this is my whole. All right, let's try a different problem, just a little bit of a twist. What is the percentage of water in CuSO4 dot 5H2O? All right, now, right away, okay, we need to quick talk about this. What is this? Okay, as soon as you see this dot H2O, this is a hydrate. So 5 water molecules have been trapped inside my CuSO4. Remember, this is just one big compound. And what I'm asking is, hey, what is the percentage of water in this whole thing? Okay, so the percent composition of H2O is really just part over whole times 100. Now again, I didn't give you any lab numbers, so we're going to use GFM. And just start by listing these. So I have coppers, and sulfurs, and oxygens, and hydrogens, and oxygens. And I have one of these, I have one of these, I have 4 of these, I have 10 hydrogens, and 5 oxygens. 64, 32, 16, 1, 16, 64 and 32 and 64 and 10 and 80. We add that all up and it's 250 grams per mole. Now, you have to be careful. What's my part? Okay, so this is the water part. This is my part. This is my whole. So I have, what do I have to do with these two numbers? That's a 10, by the way. I got to add those two numbers, so I would get 90 grams per mole divided by 250 grams per mole times 100. And it's about 36% of this formula is water. Now, make sure you read carefully, because the problem could have said this. What is the percentage of oxygen in CuSO4.5H2O? So if this was the problem, it's still percent comp equals part over whole times 100, but my part now is the oxygen. So if we go up here, what would be my part? Well, this would be, and this would be. So I'd have to take those two numbers and add them together. So we would get 144 grams per mole over 250 grams per mole times 100. And this would be about 58%. Okay, so just make sure you read carefully. Now, there's another way that we can actually use this. And it's if you're given some numbers. So let's try this. You have 174.6 grams of barium sulfate. How much barium can be recovered if this compound is decomposed? This is a percent composition problem. Okay, so I have, this is how much of the barium sulfate I have. I want to know what percentage of barium sulfate is barium, and if I know that, I know exactly how much barium I could get out of it. So we start with the percent comp problem. Right, so barium sulfate is BaSO4. So I have BAs, I have S's, and I have O's. I have 1, 1, and 4. 137.3, 32.1, and 16.0. Multiply across. 137.3, 32.1, 64.0. We add that all up. 233.4. So my part, or what I'm interested in, is my barium. So this is my part. This is my whole. So I got 137.3 grams per mole divided by 233.4 grams per mole times 100. That's about 58.83%. Well, So what that's saying is that 58.83% of this sample is barium. So how much barium could I get? Well, you can do it this way. 58.83 over 100 equals X over 174.6 grams. It turns out that I could get 102.7 grams of barium from that sample. And it's really just a different way to apply our percent composition problems. All right? All right, let's continue on. All right, so let's start with empirical formulas. So if you remember, these are our simplest form. In other words, they cannot be reduced. Well, we can actually calculate empirical formulas from the mass of its elements. There's just kind of a series of things we're going to do. So to do this, the first thing you need to do is calculate the number of moles of each element. Then you're going to divide each of these by the smallest number of moles to obtain relative amounts of moles of each element. Then we're going to write the formula using relative numbers. And then we'll write the formula using whole numbers. Okay. We're going to do this. It's actually really easy. It's not hard. But I do want to stop here for just 1 second. I want to talk about this. All right, so you see where I say calculate number of moles? There's going to be lots of math problems, okay, from here on out. We've already started doing a little bit of math, but there's going to be lots of math problems. And if you're stuck, always get into moles first. Always try to get your numbers into moles, and then work from there. All right, so try to get into moles first. Remember that. If you're stuck, get into moles first. All right, so let's go ahead and do this problem, a couple problems with this. I'm going to put this over here for now. So let's say that we have a 50.0 gram sample contains 13.28 grams of potassium, 17.68 grams of chromium, and 19.04 grams of oxygen. Find the empirical formula. Okay, so the first thing we need to do is we got to get all of these individual numbers into moles, because you can't compare grams. You have to compare moles. So the first thing we're going to do is we're going to use number of moles equals given mass over the gram formula mass. And you're going to do it 3 times. So we got to do it for potassium, chromium, and oxygen. All right, so for potassium, we have 13.28 grams all over the GFM, which is 39.10 grams per mole. So that means we have 0.340 moles of potassium. We're going to do the same thing for chromium. Number of moles equals 17.68 grams divided by the GFM of chromium, which was 51.99 grams per mole. And I'm just looking that up on the periodic table, guys, right? Okay, so here's chromium, 51.99. And that's 0.340 moles. And then we do oxygen. Number of moles equals 19.04 grams, all over 16.00 grams per mole. And we get 1.19 moles. All right, so that's our first step. Our second step is to divide these numbers. We want relative amounts. Okay, so we're going to divide, and you're going to divide them by the smallest number. Okay, so in this case, our smallest number is both 3.340. So for potassium, we'll go 0.340 divided by 0.340, and we get 1.00. For this one, we get 0.340 divided by 0.340, and we get 1.00. For this one, we're going to take 1.19, and we're going to divide it by 0.340, and we get 3.50. This is relative amounts. So now we can start to develop our formula. We have K, we have CR, and we have O. Okay, and we're going to use these numbers. So we have K, which is 1, CR, which is 1, and oxygen, which is 3.5. Okay, so this is relative numbers. We're close to being done. Okay, so we don't want any half numbers. So what can we do to get rid of that? Okay, so this is like our third step. Okay, so if I multiply through by 2, I would get K2, CR2, O7. And that would be my empirical formula. All right. Let's try another variation of this. Okay, again, there's going to be lots of variations of these, and you're just going to have to kind of figure out what you have to do. So this is percent composition to empirical formula. So this is just another type of problem that you'll see. And they're all interrelated. Okay, so I'm going to do this one by example. A compound consists of 80% carbon and 20% hydrogen by mass. What is the empirical formula? Okay, so I'm not given any numbers. Okay, so there's no numbers here. All right, so if we're getting to an empirical formula, I somehow need to get to moles. Remember, that's what we're trying to do. Get to moles. So I know that 80% of the sample is carbon and 20% is hydrogen. So in this case, what I'm going to do is I'm going to say, hey, I'm going to assume I have 100.0 grams of the compound. Now I used 100 because it's simple. I could have used 150, I could have used 7, it doesn't matter. All right? But I'm going to assume 100 because you're going to see how it makes it easy. So if I have 100 grams of this compound, well, we know that 80% is carbon. So that means what's 80% of 100? That means I have 80.0 grams of carbon. We know that 20% is hydrogen. So that means I would have 20.0 grams of hydrogen. Well, now that I have some grams, now I can convert to moles. Number of moles equals given mass over gram formula mass, or molar mass, 80.0 grams divided by 12.0 grams per mole. Turns out that I have 6.67 moles of carbon. I'm going to do the same thing for my hydrogen. Number of moles equals given mass over gram formula mass. I have 20.0 grams divided by 1.00 grams per mole, and I would have 20.0 moles. Now we're going to do the same thing that we did before. Now that we're here, we're going to divide the big by the little. Okay, so we want to calculate relative numbers, amounts. So for this one, we're going to take 6.67 divided by 6.67, and we get 1. For this one, we're going to take 20.0 divided by the smaller one, and we get 3, or almost exactly 3. Then we're going to rewrite our equation because we have 1 carbon and 3 hydrogens. They're both whole numbers already, so we would end up with CH3. And it's just another type, okay, it's another type of problem. All right, we're going to stop there for today. There's another section, something similar to this that we're going to do next time, but we'll pick up with that next time. All right? So work through some of this stuff. I got some problems for you to work with. All right, just remember, you always want to try to get to moles and go from there. All right, so have a good one.